metal, best practices in non-ferrous castings. Today we have an excellent speaker with us, actually, Mr. Anant Govind, a well-known person actually in the industry. Thank you, sir, for accepting our invitation and joining us today. So moving forward, actually, I request our chapter chairman to deliver the welcome address.
Thank you, Raj. Good afternoon to all. On behalf of Institute of Indian Foundrymen Chennai chapter, I warmly welcome you for today's technical webinar on From Melt to Metal, the best practice in non-ferrous casting. And this is jointly hosted with Hyderabad chapter. The subject chosen today is highly relevant and timely. With overall foundry fraternity, we are sure that non-ferrous sector is gaining increasing importance, driven by growing demand from industries such as automotive, EVs, electrical, electronics, aerospace, and precision engineering. Today, the industry is clearly moving towards lightweight material, improved corrosion resistance, better energy efficiency, and high performance components. This transformation, non-ferrous castings, especially aluminum, zinc, and copper-based alloys, are playing a vital and expanding role. Globally, as well as in India, we are witnessing a steady shift towards non-ferrous applications, supported by trends such as electric mobility, advanced engineering requirements, and the need of sustainable and efficient manufacturing practices. This clearly indicates that the non-ferrous segment is emerging as a key growth driver within the foundry fraternity. In this context, understanding and implementing the best practices from melt to final metal becomes extremely important. Excellence in non-ferrous casting depends on process control, alloy element, and quality consistency, energy efficient operations. And we have Mr. Anant Govind, the well-known expert in this field. And sir, we are honored to have you with us today, and I'm sure your experience and practical insights will greatly benefit all the participants. And I request all the participants to actively engage in this session and make the best use of this valuable learning opportunity. So once again, I welcome you all and wish you a webinar the grand success. Thank you.
Thank you, Sandal sir. Actually, I'll now introduce the speaker for the day. It's not required, but still I have to do it actually because Mr. Anand Bam is a well-known person actually in the industry. He was basically a mechanical engineering holding a MBA marketing from University of Pune. He is an energy auditor, certified by Bureau of Energy Efficiency. Before getting into this business, actually, he was running a chaplet manufacturing unit for almost like 9 years. And then he had his own non-ferrous foundry. And then now he's a technical consultation and energy auditing person actually from 2005 till date. So he has consulted actually for more than 100 foundries in India and abroad. And he has done energy audits for more than 75 foundries and machine shop across the globe. He has authored many technical papers presented at Indian Foundry Congress, Holocaust Asia, Pacific Conference, and Indian Foundry Journal. He authored 3 technical media on aluminum melting, metal treatment, aluminum GDC, and aluminum casting defect analysis, published by NCTS IEF. He also conducted several training programs for Tata Motors, Econ Global Sourcing, Cummins Limited, Naval Dockyards Foundry, Maruti Suzuki, Texmaco Rail Industries, and Kohler, and many IEF chapters. He has actively contributed to new product development projects with the renowned companies like BHEL, Crompton Greaves, Philips India, BRD, Kirloskar Oil Engines, and Fiat India Auto, reflecting a strong focus on innovation and value-driven solutions. He also has served as a past chairman of IEF Western Region and continues to serve the industry through various expert roles. Welcome you, sir.
Thank you, Rajmohan. Thank you, Senthil. Thank you, Chennai chapter. Thank you, Andhra chapter. And before I begin, I wish to put 2 disclaimers. First of all, I am not the only expert in the field. Hence, the practices which I am presenting here may not be really best practices, but as a coining word or rhyming word, the title is chosen as the best practices. To the best of my knowledge, these practices are good. And as Rajmohan said, they will help us in improving our efficiency, energy conservation, and reducing rejection, etc., etc. So the presentation is based on practical tips, very little or may not be uh, anything from theoretical side or phase diagram or equilibrium or metallurgy and other things. It's practical layman's long language foundry technology, which I am trying to express to everybody. So let us start with the contents that, as the title says, from melt to metal, best practices in non-ferrous castings. Okay, another disclaimer is that as per the request from Chennai chapter chairman, Mr. Senthil Kumar, this presentation, although titled for non-ferrous castings, it is basically dedicated to aluminum castings, because he said that there are hardly any foundries in southern India which are dealing in copper or brass alloys. And hence, if anybody wants such a dedicated presentation on copper alloys, they can contact me personally. I can deliver that to them in a suitable time. So moving on with the contents. First, we have to start with the inputs, that before the melt begins, what are the inputs which we are charging into the furnace? Their quality checks. The checks are before melting naturally. Then the equipment readiness, right from furnace, dies, quality instruments and others. Then the melting process, the parameters, operating range, metal treatment, and everything's impact on quality. Metal treatment itself is a very vast topic, and I have a separate presentations of about 100 slides on metal treatment. So from that, I have chosen only 4 or 5 slides in this presentation. And herein, I would like to thank Mr. Senthil Kumar and Chennai chapter for inducing me to create a new presentation. I got a call from Senthil Kumar about 2 days ago, and he asked for a presentation on non-ferrous. So the title which was discussed was this one, that made to metal best practices in non-ferrous foundry, non-ferrous castings. So I really scratched my head. I burned oil in the night and made this presentation of about 60 to 70 slides. It's a brand new presentation and every slide is prepared yesterday and today. So equipment readiness, nobody has talked about that in recent times. Melting, as I told, there is a separate topic on that. Quality checks of molten metal, mold readiness. Again, here, mold readiness, very few people have talked. Casting process, the post-process parameters impact on quality and operating range. Post-casting treatments. This is again a neglected topic, and pre-dispatch inspection. Since the presentation was made in a hurry, the slides are less than 70. And if I wish, and if I dedicate more time on it, it can exceed 300 slides. But I will fill the gap by my oration and by my narration. Next slide, please. Yes, now we come to the necessary quality checks for the input materials. For every foundry, let it be large organized foundry or a MSME foundry, the input material is basic ingots or the scrap, that is turning, boring, the foundry returns or the pot out scrap. Second important input is the fuel for combustion in the furnace or in any other equipment. Third input is treatment chemicals. Fourth is mold material, coatings, lubricants. Then comes the dye coolant, the heat treatment quenching media, and other coolants. And last but not the least are the input materials for post casting treatments, like shot blasting shots, then vibro finishing beads, surface treatment chemicals, let it be anodizing, electroplating, powder coating, painting, anything. And remember, since we are talking on the best practices from melt to metal, we have to consider all these aspects from input to output. And if we maintain quality checks right from the input, then naturally we will get a good quality output. Next slide, please. So when we talk about ingots, first and foremost, we check the quantity because that's the commercial matter. Everybody knows that aluminum is a very expensive metal, about 220, 230 rupees a kg. And recently it has touched 280 and gone back to 250, 240. So it's a volatile and very expensive metal. So even if 1 kg here and there is a big deal. So first thing to check in the input is the quantity or the weight. Second thing to check is the chemistry. Before unloading the truck, you should first verify the supplier certificate. Then cross-check with own spectrometer, or if you don't have a spectrometer in-house, then cross-check with reliable third-party lab. Take a random ingot. Every ingot has to be identified. It has to have a heat code number punched or engraved or painted on it. And any one random ingot you can take and cut a corner piece for spectro sample and check it. If you have a in-house spectrometer, it's very good. You can qualify the input quality very quickly. Once it is verified that the supplier certificate and your own spectrometer certificate are matching, every spectrometer reading may not match perfectly, but they do match to the tune of about 90-95%. So if they match about 95% from the chemistry angle, the material is accepted. Third test or a third parameter to test is freedom from inclusions. Again, it's a commercial matter as well as technical matter. Aluminum is very prone to oxidation, and aluminum oxide or the dross is a killer element which kills your profits. The same dross from commercial viewpoint, some ingot manufacturers who have dirty minds and dirty business ethics, they put into the ingots and cover it with good metal. I have witnessed some of such faulty ingots, even in Chennai, from reputed parties as well. And the best test or the very easy test is that to break any random ingot on its notch by sledgehammer. Usually, when you select an ingot, I have told that take any random ingot. There are some quick checkpoints. If you find that the ingot is casted in 1 or 2 or more layers, then you have to be very cautious because in automated ingot caster with a caster wheel and caster line, every ingot is casted in a single layer. So if there are layers, then it is casted manually. And when there is manual casting, then there is chance of adulteration or any other quality issue. When you find layers, then you are not assured of the consistency of material in it. Every layer may be from different materials. In between two layers, there can be anything which you don't want. So do not accept a layered ingot. Every ingot has to be a single piece entity. You have to break one ingot from every batch randomly at the notch with a sledgehammer, and you have to observe the fracture. I have got the photographs in coming slides. We will discuss on that later. freedom from dissolved gases. Again, you have to take a cut section by a hacksaw or a bandsaw, and you have to machine that section with a smooth machining facility by a fly cutter or by a reverse tool on a lathe, so that a smooth machined finish is achieved. And then you have to observe that smooth surface for porosity if needed by performing dry penetration test. Next slide, please. So this is the fracture test which I was telling you about. The left-hand side image shows you a fairly good clean fracture, which is of the same or similar brightness, same or similar color, same or similar grain size. On the right-hand side, you will see that there are some black or very dark gray lines or layers or patches, which indicates oxide inclusion. Although it is not intentionally put or induced oxide, this oxide is present in the ingot by the process itself because it was not filtered. Aluminum oxide appears much darker in fractured condition than the mother metal. And naturally, we are paying for aluminum and not for aluminum oxide. Apart from the commercial issue, aluminum oxide is a very dangerous element for quality of the castings. Next slide, please. There are some other defects in the ingots. On the left-hand side, you can see a gas void or a blowhole in the ingot itself. It's a harmless entity from quality point of view, but it shows that since the gas bubble is developed, the ingot mold might be wet, or the cooling water from the cooling channel of the ingot caster has entered a mold ready for casting. Otherwise, such a big blowhole cannot appear in automated ingot casting line. The right-hand side picture shows bright white spots. Can everybody see those spots?
Yes, sir.
Those spots are of
Yes.
primary silicon. It's a metallurgical defect, and it indicates that the silicon is not dissolved properly and it is present in unalloyed emulsion state, which is a dangerous condition for casting. The casting becomes brittle at that spot. Also, primary silicon attracts shrinkage voids, and hence discontinuities appear there, and the casting becomes fragile. Next slide, please. The cut section which I was talking about. A cut section of the ingot and fine machined. On the left-hand side, you can see that there is a lot of pinhole porosity in the ingot. That means a lot of hydrogen is already dissolved in the metal during casting or making of the ingot. That puts excessive load on the foundry in metal treatment of degassing. So we have to avoid such ingots and we have to reject such ingots. On the right-hand side, the machine cut section shows a very clean and smooth surface finish without any porosity or without any visible porosity. That we call as a class A ingot. So it's a good ingot, acceptable ingot, provided the chemistry and other things are accepted. Next slide, please. Now this is microstructure. Everybody may not check the microstructure of the ingots, but during fracture test, if you find bright white spots, then it's recommended that you take a micro test of that ingot. Because on the left-hand side, these platelets which you see are the platelets of primary silicon, the wafer-like things. And the needles are eutectic silicon or the dissolved silicon. On the right hand side, you can see that primary silicon is not present and only the needles or eutectic silicon is present. So the right hand side structure is more preferred, left hand side structure is not preferred. So if you find bright spots, go to the previous slide. Previous one. Yes. On the right hand side, the fracture shows bright white spots. These spots are of the primary silicon. Next slide and next slide further. So on the left hand side, the white spot magnified 400 times is the primary silicon seen as a platelet or the wafer. Next slide. If we have in-house scrap as the return or as an input material, then we have to have a complete traceability of that material during the total process life cycle. The Japanese management tools like Kanban card will help you, or a bin card, to identify and maintain that particular material, its own identity with its alloy chemistry. When any scrap or any input, let it be in-house or bought out, which is unidentified or unknown scrap, the best way is to mix it thoroughly. If you have got 100 bags of turning borings, then empty them all on a floor, clean floor, mix them thoroughly, take a 1 kg sample, melt it in a small crucible or in a small furnace or with a gas burner, take a spectrocoin from that and check its chemistry. That will give you average chemistry of that unknown turning boring. If you have solid scrap which is unknown, then go by the geometry of the scrap. You can identify that this is the same casting or this is the same geometry of the casting, and hence you can prepare a lot of same or similar castings and then randomly check 1 or 2 pieces from that lot. The purpose of this is that do not melt anything unless you know its chemistry. Even your own runners, risers, and rejected castings, they have to have their own identification by way of color code or by way of any other means of identification, alloy identification. Next slide, please. So this is the, what you can say, a symbolic view of turning boring scrap. Never use unidentified scrap because it may open a Pandora's box. Next slide, please. Now, after the input metal, we move on to the second input, that is fuel for the furnace. Many foundries have bulk melters or scalar furnaces. Even some small foundries have oil-fired or gas-fired furnaces. For gas-fired furnaces, you get a self-certification from the supplier that the calorific value of the gas which is supplied to you during this fortnight is XYZ. And they give you an average of every day, a daily average submitted to you on a fortnightly basis. That's the standard quality system of every gas supplier. From the LPG supplier also, you get a calorific value certificate. For the liquid fuels, which is LDO or furnace oil or diesel or LS, what is that? LSHS. Nowadays, LSHS and FO are not preferred because of the pollution control norms. LDO is quite popular. So first again, check the quantity. Then check the viscosity or the density. Check the calorific value. If you don't have a calorimeter, then ask for the supplier certificate and randomly get the calorific value checked from a NABL accredited lab. Check for contamination. If you are using heavy oils, that is furnace oil or LSHS, then water contamination is quite likely. And it usually happens at the retailer location, not from the oil company itself, but the retailer may mix or adulterate it with the oil. Or sometimes, if the oil storage tank is underground, then during monsoon seasons, water may seep into the tank. Due to the high viscosity of heavy oils, the water gets emulsified and it is present in it. It doesn't settle down quickly. So to check water, take a sample, preferably by dipping a wick or a cloth piece right up to the bottom of the container and burn that cloth piece. If water is present in oil, during burning, that cloth will create a crackling sound. फटाके जैसे फूटते हैं वैसे आवाज आएगा, फट 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 चर 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 ऐसे. So if that crackling sound is heard during burning, it is a clear indication that water is present in the oil. Other contamination or most popular adulteration, I would say, in furnace oil is the used motor oil, which contains fine metallic dust as well as carbon particles. And the best test to check it is put a drop of it on a filter paper, if possible with a thinner. Then if dirt, metallic contamination or carbonaceous matter contamination is present in the oil, then that is retained above the filter paper and the oil along with thinner passes through the filter paper. So these 2 or 3 tests will qualify your input material, which is furnace oil or fuel for your own furnace. Next slide, please. Treatment chemicals. I see that there are 2 people from Seraflux group attending this meeting. Somebody from iTech, then Mr. Gajanan Kadukar, and mostly Mr. Dhumal is also there on the line. So they will understand it very well. Because majority of treatment chemicals, which are salts, are hygroscopic in nature. Secondly, some proprietary treatment chemicals, which are mixtures of a variety of salts and other chemicals, they have their own internal reactions going on as well. Hence, every chemical has got its own shelf life. So first and foremost, before accepting any treatment chemical, check for the expiry date. If you are getting a lot which is close to its expiry, then ask for a hefty discount and consume that lot within the expiry period itself. If you are not able to consume it, then there is no guarantee from the supplier side for the performance of the chemical. Next is naturally check the quantity. Then ensure dryness of powder flux or tablet or pressed tablet of any degasser or other chemical, because these are hygroscopic materials. Usually all these materials have got their own color, and if they absorb moisture, then the color darkens substantially. So observe for the color of the chemical also. If any moisture is present in it, then it will not be free flowing. It will form a lump. So ensure dryness of the powdery flux as well as tablets. When you are buying master alloys, metallic inputs, then ask for the test certificate of those alloys from the supplier. Occasionally cross-check the quality through third-party reliable lab. Now for checking master alloys, usually spectrometers cannot check that concentration of master alloy. You have to go for weight analysis. And for that, you have to contact engineering colleges, or there are very few labs which do weight analysis of master alloys. So you have to be careful about it. And hence a trusted source is always preferred. Next slide, please. Next input material is sand for molding as well as core making. It has got direct impact on the surface finish of your product. It has got direct impact on the quality of your outcome apart from surface finish by way of its permeability, by way of its loss on ignition or gas generation, by way of its binding properties, and many such things. First of all, for the sand, check the sieve analysis. If you have got a macroscope or a stereo microscope, then check the angularity. If you have got facility, then check the silica content or go for the supplier certification. From the binder side, if you are using organic binders, then with the resin and hardness system, you can have a quick shop floor test by preparing a sample, maybe 100 grams of prepared sand. You can prepare it, put it into a random mold, and check for the stripping time, the setting time, and curing time. Then check for the hardness of that particular prepared sample. If you have got a sand lab, then there are further more tests like tensile strength, then stick point test, and others. If you are having a green sand system, then apart from sieve analysis, angularity, and silica content, you have to check the gelling index of the bentonite, LOI, moisture content in the prepared silica sand, and many other tests are there. Next slide, please. This is a sample of sieve analysis. If you have got a single peak, then that sand is of average quality. And if the peak is at the same point, but the graph is moving gradually up like a bell-shaped curve, then it's slightly better or a good quality of sand. Next slide, please. Coatings. Coatings are applicable to sand mold, sand core, as well as to the die surface. Coating is the final element which delivers its own surface finish to the casting. But before that, its primary function is to create a barrier surface between the metal and the mold. To prevent the metal mold reaction, coating is necessary. So for any coating, the first and foremost test is density test or viscosity test. And a quick test can be checked by a B4 cup or by a buoyancy meter. Next slide, please. This is an image of B4 cup. It's a conical cup and with a aperture or a measured hole on the bottom. The volume is also known. There is a marking. There is a stand, and you have to use a stopwatch along with it. So the process is that put the cup on the stand, put an empty vessel at the bottom, hold your finger from the bottom of the hole on the cup so as to plug that hole, pour the prepared coating into the cup up to the marking line, and simultaneously release your finger from the bottom hole and start the stopwatch. You have to measure the time at which the cup gets empty. So usually it is expressed in seconds. Say before cup timing 18 seconds, 20 seconds, 24 seconds, like that. So if it takes lesser time, that means your coating is thinner. If it takes more time, that means your coating is on a thicker side. The thickness or viscosity of the coating is function of the quality and the desired effect which you want from the coating. Thicker coating delivers you a a higher thickness of the coating in less time of application. But there is a chance that due to its thickness, it may not reach or it may not penetrate to the finer details of the mold or the die. So the feature sharpness will be poor, but the coating thickness will be substantial. Whereas the thinner coating will reach to the finest details of the features, but the coating thickness will be quite thin. For example, the white coating, which we call as a die coat 140. If it is having a viscosity of before cup 20 or 22 seconds, then in a single application, it can deliver a coating thickness, a dry film thickness of 100 plus microns, 100 to 150 microns. The same coating, if the P4 cup empties in 16 seconds, then it will deliver a thickness, a dry film thickness of maybe 50 to 70 microns. So the coating thickness, the film thickness is a function of viscosity of the coating. And hence, it is very important to check viscosity of the coating. And B4 cup is the very easy, very rugged and quick shop floor test. This image is taken from internet, from Amazon site, and the brand is Labico. So I have to mention that to prevent from any copyright pilferages. Next slide, please. Lubricants. For high pressure die casting, everybody is using lubricant. The main function of lubricant is again to prevent soldering. And the secondary function is to have thermal balance of the die surface. Even today, a lot of foundries or majority of the foundries are using mineral oil as the basic lubricant and emulsified in water, maybe 1%, 2%, 5%. The dilution depends on the manufacturer's recommendation and intricacy of your casting. So first and foremost, check the dilution of lubricant. And rather, it's very difficult to check the dilution. So you have to ensure a process of making correct dilution of the lubricant. You have to prepare a recipe by which the recommended dilution of the lubricant can be achieved. I have witnessed a case in a very reputed foundry making more than 10,000 tons a month of aluminum pressure die casting. And they are not monitoring the dilution of lubricant. There was a complaint of frequent soldering, and blackening of the die surface. So when I went there as a consultant, I observed that the dilution of lubricant was on a random basis. A bucket full of lubricant put in a barrel, and a person counted 8 buckets, 9 buckets, 10 buckets. Then he forgot the count. Then he started from 13 again. And in a very haphazard manner, it was prepared. Then like a person in a kitchen checks consistency of the sambar or the tea, like taking it on hand, and by this, he was checking the dilution by hand. So naturally, the lubricant at times failed to create a barrier, and hence soldering was quite frequent. When there was a case of soldering, the same operator, put another bucket into the same barrel and doubled the concentration, which was again not desired. So that high concentration lubricant created a charring effect on the die surface, thereby blackening the die. So the cycle or the vicious circle was continuous. When a system was set of measuring the mother lubricant and measuring the diluting water, measuring the TDS of the diluting water, quality of the water, and using filtration before passing it onto the lubricant pump, these defects were gone. Next slide, please. Now for the coolant or for the quenching media of the heat treatment furnace. First and foremost is to check for TDS, total dissolved solids, or the salinity of the water. Excess TDS will lead to salt deposition, calcination, and loss of cooling effect in the cooling line. Again, any salt or contamination in the quenching media will lead to discoloration or blackening of the casting after heat treatment. And once the casting blackens during quenching, it is very difficult to get back its own white luster. So you have to be very careful. You have to maintain, or you have to use preferably demineralized or DM water for quenching media as well as in the cooling lines. Next slide, please. Now we move on to other input materials which are for the post casting treatments. Shot blasting, glass bead blasting, vibro finishing, and other surface treatments. For aluminum shot blasting, stainless steel cut wire shots are highly preferred. I recommend them because they last long and they do not break easily. They do not deliver its own color onto the casting. Preferable size is 0.3 mm to 0.7 mm for aluminum and 0.5 mm to 1 mm for copper alloys. How many of you are using a mixture of 2 or more sizes of shots? Please comment or please raise your hand. I want this session to be interactive. How many of the audience is using a mixture of 2 or more sizes of shots in shot blasting? Hello, I want an answer from your side, sirs. If you are not using a mixture of different sizes of shots, type that we are not using. But let the session be interactive. Okay, I got one answer that they are not using mixed shots. 0.8 mm, not using. Very good. So that means that people are not sleeping. They are attentive and they are answering to my questions. Thank you very much, gentlemen. Now I explain the theory of principle of multiple reflections through differential depth of valleys. When you use a single size of shots, during shot passing, the surface gets small or tiny dents. All the dents are the valleys, depressions, of the same size and which are distributed equal or evenly on the surface. Whatever is the sunlight coming from whichever side, it is getting see when we use for sizes
Sir, the voice is breaking, sir.
what is that? Uh, when you use two front size of operations. 0.7 mm shot will create larger
Are we getting right voice?
on the surface.
Hello? It looks like there's some disturbance, sir. Any the voice is clear?
Sir, your voice is clear, sir.
Speaker? I'm not able to hear him properly.
He's checking. He's The trainer will reconnect, sir.
Okay. Shailesh, have you spoken to speaker or phone?
What do you say?
Huh?
We are talking currently, sir. We are talking with him.
Yeah.
Yes, sir.
Sir, he is rejoining, sir. It will take 1 or 2 minutes, sir.
Shailesh, what happened?
Network connection, he is joining by mobile.
Okay.
Hello? Am I audible now?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Something has gone wrong, so the bandwidth
Yes,
was
sir.
very
Yes, sir.
low. Now I have joined on mobile phone. So I was talking about the short blasting and the benefits of using mixed shots. When we use mixed shots, then the indentations or the depressions created on the surface by shot blasting are of mixed sizes. And that creates multiple reflections of the incident light. These multiple reflections make the casting brighter and more lustrous, like a satin, metallic satin finish. And hence, if possible, I recommend using such mixture of shots. The finish which you get is out of this world, and you will fall in love with that finish. Nothing wrong in using single size of shots, but using mixture of shots is a next level of quality or delivery in surface treatment. Next slide, please. Now we come to sandblasting. Sandblasting is a different process. It needs to have an enclosure with a dust collector and all those things. It is, although the shot blasting machine also has a dust collector, the creation of fines is very little in shot blasting, but the creation of fines or the dust creation in sand blasting is very high. And hence, the dust removal or dust extraction is the most critical phase in sand blasting. The recommended sand is silica sand. Any silica sand can do, but preferred is crushed quartz due to its slightly higher hardness, and due to artificially manufactured, it is more angular, more sharp, and hence it creates a smoother surface in a shorter time. Second point, use good dust collector, as I said earlier. Third point is very important. The dust adheres to the casting or the surface which we are trying to clean. Hence, post sandblasting, the next slide, please. In for vibratory finishing or vibro finishing. Usually, artificially manufactured ceramic beads are used as a media for vibration, along with soap or shampoo or any alkaline fluid. Why alkali? Because alkali or mild alkali reacts with aluminium, removing the oxide film deposited on the aluminium and helping in attaining a neutral or a electrochemically neutral layer on the surface of the casting. Again, since we are using alkali, after the vibro finishing, it is recommended to have a good thorough washing of the casting to prevent any alkyd generation or any white rust formation or any pitting of the casting surface. When we are using any natural stones or pebbles, then make sure that those are round or rounded and they do not have any sharp corner or sharp edge. Next slide, please. Now we come to the equipment part of it, equipment readiness. Remember, we have not started the casting process as yet. Our list is going on the input side, even now, to the equipment. First inspection is for the furnace lining. Second is for the crucible condition. Third is for burner cleanliness. Then oil preheater and pump unit operation, filter operation. Then if you are using resistance furnaces, then condition of coils, their connections, their maximum current drawing capacity. Then along with the furnaces, we have thermocouples and temperature indicators and the PLCs to control or operate the furnace based on the inputs from the thermocouple. Then we have the degassing unit. Then we have got other quality instruments like reduced pressure test apparatus or density index apparatus and any other quality instrument. Next slide, please. Check the lining of furnace for any likely crack or worn out lining or damaged lining if you are using induction furnace. Then repair it immediately if observed. Monitor the lining life and change the lining at recommended number of heats or recommended number of hours of operation, irrespective of condition of lining. This becomes a part of total preventive maintenance, TPM. If you maintain the lining in its good condition, then naturally the downtime of the equipment is zero. Next slide, please. This is a photograph of a cast iron furnace, induction furnace with a very dirty condition of lining. The lining is worn out in multiple locations. There is a lot of slag adhering to the faults or the cracks or the worn out part of the lining. And such lining is thoroughly or totally unreliable, and it is an invitation to major accidents. Unfortunately, I could not get a photograph of aluminum melting induction furnace lining because there are very less number of induction furnaces in aluminum melting. Next slide, please. Crucible condition. Before starting, check the crucible for any cracks. Check for oxide buildup. And it's a frequent check or routine check. All the checks are daily checks or every heat-wise checks. Before you put in any new material, check the crucible condition, check the oxide buildup, check the thermocouples, oxide buildup on the thermocouples, check other equipment like ladders, spoons, or any hand tools. All the checks are routine and daily checks. There is no escape to it. Then monitor the crucible life by hours of use or number of heats. Change the crucible after recommended life, irrespective of its condition. Because if the crucible cracks or fails during operation or during working, then it becomes a very big mess to clean the furnace. It may invite short circuit. It may invite accidental shocks to the operator. And the repairs or the damages of a broken crucible during operation take few days. Instead of that, if the recommended lifespan is over on a weekly off, just change the crucible even if it is apparently good or it is looking good in working condition. That will prevent all these pitfalls, and it's again a TPM activity. Next slide, please. You have to observe this photograph carefully. On the very top side is the crucible edge, and the white and the gray thing which you observe is the oxide built-up. It's about 1 inch thick oxide built up on a crucible. It's a 300 kg crucible. The outer edge of the crucible is not visible in the picture. The inner edge of the crucible and the top ring is visible. And inside there is a black line, which is the gap between the oxide and the crucible lining. And in the center, you can see the empty bottom of the crucible. So if such a thick oxide lining is present on the crucible, It keeps on dissolving into molten metal, thereby creating oxide inclusions in your casting. That's a serious quality threat. But apart from that, aluminum oxide is a bad conductor of heat, and hence the thermal conductivity of crucible reduces drastically. And hence to melt the metal, you require more and more energy input. That becomes unviable. Next slide, please. Burner cleanliness. Check the burner nozzles daily and clean them thoroughly. Check the airflow diaphragm or the baffle and its adjustments. Check blower pressure and flow. And after all that, finally adjust the flame to reducing atmosphere and correct dwell time. I got a photograph for that. I will explain that into that slide. Next slide, please. This is front view of the burner. You can see that it's quite dirty. And along with oil, there is a lot of dirt or carbon adhering to the burner. And one needs to clean the burner daily. You should not wait for the burner to have such dirty deposit on it. Next slide, please. This is a view of a pit furnace, oil-fired pit furnace, wherein the color of flame is white to yellow. So this is an indication of reducing atmosphere. Whenever the atmosphere is reducing, that means the flame is not blue. The flame is white to yellow. Then the reducing atmosphere helps in reducing the melting losses. It helps in maintaining the metal in its metallic condition and preventing further oxidation of the metal. That's the first point. And second point is that a very little amount of flame is coming out from the aperture of the lid. That means that the flame is taking its maximum time inside the furnace chamber, and a very little of it is going out by way of flue. So this is an indication of efficient operation along with reducing atmosphere. Next slide, please. Oil preheater and pump unit. Check the temperature of input oil. If found less, then change the heater cartridge. Clean the oil filters daily. Check the oil atomization at burner nozzle before firing. You can see that a black stream of oil, it should come out like a spray painting nozzle. There should not be big droplets or a stream of oil. There should be fine atomized particles of oil coming out from the nozzle, and it should be like a spray painting appearing on the furnace. Then start the firing. Ignite the flame and check the flame throw with oil flow adjustments. Ensure that the flame comes out just a little from the furnace, even if it is a tower furnace or a chamber type furnace or a pit furnace or a tilting furnace. Everywhere you can observe the flame coming out. So it should not be a big flame coming out, and it should not be absence of flame coming out. A very tiny, slightly visible flame should come out from the exit, and it should be white to yellow. Again, if it is a chamber type furnace, then the throw of flame should be on the desired position and the desired location. If it is a crucible type furnace, then the flame should swirl or swing around the crucible for minimum 2 to 3 times. And after whirling 3 times or more, then it should come out from the top lid. All these things you have to monitor daily. And the flame color or the air fuel ratio and the volume and pressure of the air. Both of these things determine the reducing or oxidizing atmosphere as well as flames throw and flames dwell time. So you have to adjust both, not only the fuel flow, but the airflow as well. Next slide, please. If it is a resistance furnace, check the coil condition. You cannot check the coil condition visually every now and then because the coils are enclosed in the furnace. But you can determine or you can predict the condition of coil indirectly by the current drawn by the furnace. When the furnace is new, for example, if the current drawn is 200 amperes, then that becomes your benchmark that the coil should be drawing 200 amperes. The moment it reduces to 180 amperes or further less, then it becomes a matter of concern. The moment it reduces to 15% or more, then it's time to change the coils. Because such a reduction in current carrying capacity happens due to oxidation of the coil element or the kanthal metal in the coil. Next slide, please. This is a typical view of electric resistance furnace before fitment of the crucible. You can see that the ceramic foam or Ceravul lining is in very good condition, as well as the heater elements, the coils are also in good condition. Next slide, please. Another readiness is of the equipment, that is thermocouple and temperature indicator. Check for the oxide built-up on the dip type thermocouple. Check the calibration certificate of the thermocouple and the indicator system. Check all the connections. Check reading on the indicator and frequently verify the indicator and thermocouple by another handheld portable pyrometer. Both the readings should be within 1 or 2% of each other. Then it's a certificate, self-certificate that your system is running in good condition. Next slide, please. Here is a photograph of dip type thermocouple having a very large deposit of oxide on it. And again, as I told, these oxides keep on dissolving into metal, thereby making the metal dirty. Again, it's a bad conductor of heat. So the reading which is taken by the thermocouple is a false reading. The metal might be quite hot than the reading shown by such a thermocouple. Next slide, please. Now we come to the degassing unit or the rotary degasser. Check the condition of rotor. Replace the rotor as soon as found worn out or damaged. Again, this third point is very important. Always clean the rotor immediately after degassing when it is red hot. Because the oxide which is deposited on the rotor along with the metal, aluminum metal, it is in soft condition, porous condition till the time it is red hot. You can remove that with scraping, by scraping with any hand tool like a long blade or a long strip, and it will keep the rotor clean. If it is not cleaned when it is red hot, then after cooling, the oxide becomes corundum. And that's a very hard material. You cannot remove that. If you try to remove that, the rotor will break. Next slide, please. Wait. Check the vortex formation and adjust RPM accordingly. You have to ensure that a clean vortex is formed. The vortex should be visible. And a thumb rule is that whenever the vortex is formed, the eye of vortex goes to a depression and on the side walls, the metal rises a little bit. The level difference between the sidewall and the eye of vortex should be approximately 4 inches or 100 mm. That's a thumb rule of formation of a good vortex. You have to adjust the RPM of rotor till you get such a good vortex formed in the crucible. Next is check the bubble adjustment. Check the bubbles and adjust the flow and pressure of the inert gas. The bubbles should not be visible. There should not be a burp or blup of a big bubble coming out. Aluminum metal should not splash out on the top of the furnace. And again, a thumb rule is that as per theory of bubble formation and effectiveness of the bubble size should be between 1.5 and 3 mm. But nobody can really measure that size inside molten metal. But by thumb rule, if such bubbles break on the surface of the molten metal, then naturally very tiny aluminum metal particles are spattered outside the furnace, outside the crucible, and they get collected on the top of the furnace lid or furnace cover. These particles, which are collected on the top of the furnace, appear like suji or semolina. In Marathi, we call it rava. In Hindi, call it suji. And it appears like very small short blasting shots, maybe 0.3 to 0.4 mm size. And if you find such metallic particles on top of the furnace, then rest assured that your bubble size is perfect. And with such a vortex of 4 inches level difference between sidewall and the eye of the vortex, and deposition or collection of fine particles of metal on the top of furnace are the two indicators that your RPM of the rotor is good and your bubble size is good, and you attain maximum efficiency of degassing in such a condition. Next slide, please. This is a photograph of the dirtiest rotor I have ever seen. I have to tell you that this is a rotor. The white thing which you find inverted T-shaped. It is the rotor of the degassing machine. And I cannot see any fin or any rib. All I can see is just oxide, oxide, and oxide. Thoroughly deposited for ages. Naturally, the whole of the shaft is also clogged. Nitrogen or argon is not coming out. This thing is not able to churn. And hence, degassing is just for a show. Again, it's a first-hand information. I was a consultant there. I was called for a day that degassing is not effective. Even after doing degassing for 2 hours, our density index is not coming within the range. Kindly advise us. And the matter was solved at the first site itself. If you have got such a dirty rotor, nobody on this earth can degas your material. The best way is to change the rotor and then onwards maintain the rotor in good condition by cleaning it every time it comes out from the furnace. Next slide, please. Equipment readiness of reduced pressure test apparatus, density index apparatus, and other instruments. Check oil level of the vacuum pump. This is the first and foremost check. The oil in the vacuum pump is like blood in your system, blood in your body. The moment the oil level in the vacuum pump drops, the veins of the pump start rubbing on the surface. And after such a rubbing, maybe in a 1 hour or 2 hours of rubbing, the pump fails. It fails to create vacuum. And why? Because somebody did not top up the oil. It is not a frequent top up. The requirement of oil is hardly 300 ml. And the top up required is maybe once in 6 months or so. But if you don't top it up, you lose the pump. Second is that check the vacuum gauge and confirm vacuum formation. Start the vacuum or the reduced pressure test apparatus without any metal or without any sampling crucible within it. Close the lid. See that the vacuum gauge is indicating vacuum. Try to lift the lid at 80 millibar partial vacuum. No person by its own hands can lift the lid. The vacuum created is so strong that if you try to lift the lid, the machine, the whole machine, 50 kg, 100 kg machine gets lifted along with it. So that's a simple test of effectiveness of vacuum creation. Check the sampling cups and the coating on the cups. Keep the tongs or pliers ready, handy, because once the sample is poured and it is solidified, you have to take it out for measurement. Check the water level in the beaker or the immersion chamber, whatever you have in the density index apparatus. Check the zero on weighing scale. And for other apparatus or other equipment, check the condition of hand tools, ladles, and the coating on it. Because usually the ladles or hand tools are made of mild steel, which is a ferrous material. And iron is the biggest enemy of molten aluminum or aluminum castings. And iron dissolves readily into molten aluminum. So every hand tool or everything whichever goes inside the liquid metal has to be thoroughly coated. Next slide, please. Now we come to principles of melting. Melt the metal as quickly as possible. Melt it with minimum energy consumption. Achieve complete solution of alloying elements or any top-up materials. Melt the metal in as clean condition as possible. Keep it gas-free. Avoid overheating and minimize melting loss. Everything of it is very well explained in my earlier presentation on melting and metal treatment. So only this one slide I have taken from that. I'm not going to explain it further because we have already exceeded the scheduled timeline. Move on to next slide. While starting the melting in the empty crucible, one has to take care that ingots have to be placed vertically and they have to be loosely packed, not closely packed, because before melting, the ingots expand. There is thermal expansion of aluminum. And if the ingots are not loosely packed, then that expansion adds on to one onto other, and literally it leads to cracking of the crucible by thermal expansion. So ensure that the ingots are stacked vertically and they are loosely packed. Next slide. We go on to metal treatment. Again, only one slide from the previous metal treatment presentation. First, metal treatment is cleaning. It is usually done by flux. But in recent times, Japanese foundries are avoiding fluxes and they are moving to inert gas or vacuum melting to avoid oxide generation itself. Why do we need to clean the metal? Because either the ingots or the input material itself is dirty, or there is freshly induced, freshly created aluminum oxide during the melting process itself. Hence, we have to clean that oxide. We have to separate that oxide from the metal by applying cleaning fluxes. So if the metal is clean initially itself, do we really need to clean it? Again, the answer is no. So the Japanese have moved ahead and they have avoided fluxes by way of vacuum or inert gas melting. Some foundries in India, especially Maruti Suzuki, are trying that method and they have succeeded substantially in it. But even now, even today, they are not able to eliminate flux. They have reduced consumption of flux drastically, but still they have not eliminated it. But very soon it will happen. Second process is degassing. It is done by tablet degassing or by inert gas application. It can be by purging inert gas or by rotary degasser. Third process is grain refinement. It can be achieved by addition of salts or metallic grain refiners. And last treatment is modification. It is again by addition of salt or by metallic modifiers. I have got one slide each of each treatment. How? Okay. What is the purpose of treatment? Cleaning basically removes oxides and reduces oxide inclusions. Degassing reduces or eliminates hydrogen, the only soluble gas in aluminum, which is the cause of pinhole porosity. Grain refinement refines the grains or makes the grains smaller. It leads to increase or improvement in ultimate tensile strength, and it helps in reducing shrinkage porosity. Modification of silicon increases or leads to better elongation, and also it helps in giving quick response to heat treatment. Next slide, please. Next slide. Okay. These are photographs of macro structure. Every sample is 40 mm diameter. On the left hand side is without grain refinement. On the right hand side is with grain refinement. Next slide. This ASM grain size classification number. Number 1 is finest grains. Number 6 are the coarsest grains. As per ASM macro grain size classification, there are 6 varieties: 1, 2, 3, 4, 5, 6. These are to be checked on macrograph of 40 mm diameter sample. You take a fine machining cut on it, or you scrape it on a belt grinder, and then perform etching by macro agent, either HF or preferable etching agent is Tucker's etch. Next slide, please. These are microstructures or micrographs depicting modification of silicon. On the left hand side is unmodified silicon. Acicular silicon is seen. On the right hand side is fully modified silicon along with alpha dendrites. Next slide, please. This is ASM classification of levels of modification. Level 1 is unmodified. Level 6 is super modified. Practically achievable levels are level 3 and 4. With little difficulty and good quality control, level 5 is also achievable. But level 6 can be achieved only in laboratory scale. Also, it is not required in any practical application. Even for aerospace application, level 4 or level 5 modification is recommended. Next slide, please. Quality checks of molten metal. Preferably, you should have a temperature log. Then you should have chemistry report record. You should have density index record. And you should have K mold record. Next slide. When you are refining the material by titanium and boron, the effectiveness of grain refiners vanishes after high temperature, maybe exceeding 780 degrees Celsius. And that change is irreversible. The titanium is visible in spectrometer, but it fails to refine the grains. So you have to ensure that in the life cycle of casting, that is from solid to melting to holding to treatment to casting again, it has not crossed 780 degrees Celsius at any point of time. That is why it is important to have a temperature log or to have a permanent dip type thermocouple connected to PLC, having a direct shut off control on the furnace. And the range should be set in such a way to allow certain buffer zone. Because the furnace lining is usually at 900 or 1000 degrees Celsius, the coil temperature. The metal is at 730, 740, 720 degrees Celsius. So the delta T, the temperature difference, is to the tune of 300 degrees Celsius, 250 to 300. The heat transfer, formula for heat transfer is mCp delta T. So M is the mass. So mass of the lining, if it is ceravul lining or ceramic foam lining, the mass of lining is very small, maybe 100 kg or so. But for a 500 kg metal, 100 kg lining at 900 or 1000 degrees Celsius will be sufficient to raise the temperature by 20 or 25 degrees Celsius. But if the lining of furnace is of brick lining, then the mass of lining is to the tune of 1000 kg. And 1000 kg at 1000 degrees Celsius, transferring heat to 500 kg at 720 degrees Celsius. Even after putting off the coils, that heat load is sufficient enough to raise the temperature by 100 degrees Celsius. So you have to have sufficient buffer zone to put it off as quickly as possible so that the temperature of metal does not rise to more than 780 degrees Celsius at any given time. Next slide, please. Chemistry. Every casting qualifies to customer acceptance only if chemical composition is within prescribed limits. Check button samples for spectrometry before the metal treatment for the basic chemistry, basic elements. If found acceptable, then only proceed for metal treatment. Otherwise, balance the chemistry by alloy addition or by diluting, as the case may be. Cross-check final chemistry after treatment for verifying titanium, boron, sodium, strontium, or whatever you have added as metal treatment element. Sufficient percentage of titanium and strontium ensures grain refinement and modification. Next slide, please. A typical spectro button. Next slide. Check density index before pouring and at every 30 minutes intervals during holding. For commercial applications, density index should be below 10%. For leak-proof engineering castings or structural castings, density index should be below 5%. For critical castings or helium leak-proof castings, density index should be between 1% and 3.5%. For electric conductivity and aerospace grade castings, density index should be below 1.5%. Next slide. These are typical cut sections of reduced pressure test samples or vacuum samples, commercially called. The left-hand side is top left is density index 1.5%, and bottom right is density index 16%. Next slide, please. K mold. The K value should be checked and maintained below the prescribed value. Every customer should be recommending you that K value should be so and so. Ideally, the K value should be 0. Not to forget, one has to preserve all these samples, spectrobutton, then density index samples and K mold samples for the time prescribed by the buyer or for a minimum of 3 months. Next slide. Next slide, please. Top left is K mold, both parts, top and bottom part. Bottom left is the casting coming out from the K mold. To the right hand side are the K mold fractures. Next slide. It is a tensile specimen, tensile test bar. Every heat for a critical casting or for safety critical castings or for any government of India undertaking castings, let it be railway or any PSU casting. Minimum 3 test bars per heat are recommended. This is a sample of separately cast test bar. Sometimes you have to cast an integral test bar. Sometimes you have to take a test bar by cutting a casting, sacrificing that casting. It depends on quality requirements of your buyer. Next slide. Now input inspection for sand casting. Check quality of sand. Check the mold hardness. Check for smooth, hurdle-free surface and non-friable edges. Next slide. For resin coated sand, there are other tests like tensile test, hot tensile test, stick point, apart from the standard sieve analysis. Next slide. Typical photographs of shell core making, then core setting, and dip type core coating. Next slide. In case of die casting, you have to monitor die temperature, the die coating and its thickness, and cleanliness of the vents. Next slide. 99% of the times, die is preheated by gas burners. In case of pressure die casting, the thermoregulator takes care of it. Next slide. You have to monitor and record die temperature frequently. Next slide. On the left hand side is spray coating on a hot die surface. On the right hand side is application of thick coating or riser coating by brush. Next slide. Next slide, please. Okay. On the left hand side is a typical photo of wet film thickness gauge. This is a hexagonal gauge. You can also get a rectangular gauge having one side or two sides of gauging serrations. On the right hand side is the dry film thickness measurement apparatus, which is ultrasound or not ultrasound, it is a magnetic gauge. Next slide, please. Okay. For the clean vents, I did not get any photograph, but if you have got access to our IIF NCTS CDs on gravity die casting, there is a separate chapter on venting. So you can go through that. Next slide, please. Remember 4 T's in any casting process. Let it be ferrous, non-ferrous, aluminum, copper, anything. These are the 4 T's which govern the casting process. Time, temperature, treatment. These are 3 scientific T's which can be controlled, which can be monitored. But the 4th T, which is temperament of the operator, it is not controllable. So you have to deal with it and move on to automation of the process as quickly as possible to eliminate this 4th T, or the human factor of rejection. Next slide, please. Other protocols, quality checks, shot blasting, check the shots, check for the fines, sand blasting, check the fines, vibro finishing, check the concentration of alkali, as well as periodically clean the pebbles, electrochemical cleaning, ultrasound cleaning, check the effectiveness of apparatus, periodically filter the medium, anodizing, powder coating, painting, electroplating. All these post-casting treatments have got immense importance for cleanliness and concentration of each and every element. Next slide, please. Pre-dispatch inspection. Let it be gauging, physical measurement, or manual measurement. It has to be done and it has to be recorded. It has to be documented as per the ballooning drawing. And then your responsibility as a foundryman ends. Next slide. Thank you for patient listening. And if time permits and if the chapter permits, you can ask questions.
Sir, anyone has any questions?
Sir, hello, sir. This is Kalmax from Ditech India.
Yes.
Sir, first of all, thanks for this wonderful session. Actually, I am the fresher for this field. I can able to learn many new things, but I have to know the reason for electroplating of the post process of casting, sir. May I know the reason for the electroplating?
Electroplating is a very common process for many aesthetic components. For example, diamond cut alloy wheels, it is electroplated. It is chrome plated. So the reason for
Oh, yes, sir.
electroplating
Okay.
is as per the customer requirement. If the customer
Okay, sir,
wants
as
it,
per the
if the customer wants it electroplated, it has to be electroplated, na?
okay, sir. I think it is for the smooth surface finish or the aesthetic look of casting, sir.
No. It has nothing to do with surface finish. Electroplating is a deposition of another metal on the base metal by electrochemical application. The thickness of electroplating is measured in few microns, up to 20 or 30 microns, not more than that. So it doesn't improve your surface finish. The surface finish is determined by your casting quality or the machining quality itself.
Okay, sir. Thank you.
Yes.
Anant sir, there was a question in the chat box. They said actually, can you please elaborate on K-type mold testing, please?
Okay. K-mold is a patented process by a Japanese scientist. And if you Google it, you will find it, the patent document itself. It's a 40 mm by 6 mm by 360 mm plate being casted on a 30-degree slant face, having 5 notches. And the principle is very simple. Wherever the metallic flow changes its direction, the probability of inclusions getting caught at that point is very high. If you observe water flowing through a gutter or a canal, then at every corner, the lot of leaves or any plastic dirt, it gets accumulated wherever corner is there or wherever the flow is changing its direction. Similarly, whenever the metallic aluminum changes direction of the flow, at that location, whatever is the inclusion, whatever are the oxides, they get caught. And hence, these oxides are caught at the notches of the K mold. You have to break the sample of the K mold after solidification. And you have to observe those fractures for the visual analysis or on image analysis software. And you have to measure, physically measure number of dark spots. Every dark spot is a inclusion. So if you, as I said, there are 5 notches. So there are 10 fractured surfaces. And if you find all those 10 surfaces together, if you find 10 dark spots, then the dark spots observed are 10 divided by number of surfaces, that is 10. So the K value is 1. If you find 5 dark spots, then the K value is 0.5. If you find 20 dark spots, then the K value is 2. Smaller the K value, cleaner is the metal. So ideally, the K value should be 0. Your casting should be inclusion free. That is the purpose of K mold. Any other question?
Sir, there's one question from Mr. Pradeep. Actually, he asked about for hyper-eutectic alloys containing 17% silicon. How can you bring the temperature below 780 degrees Celsius?
Remember one thing, when it is 17% silicon, it is hyper-eutectic alloy, not hypo. So hyper-eutectic alloys are modified by way of phosphorus, not by strontium. And the grain refinement by titanium often fails for hyper-eutectic alloys, and you have to go for chill casting for attaining grain refinement. 780 degrees Celsius, as I specifically said, is applicable only for titanium treated alloys. And if you say silicon is 17%, then titanium is of no use in that alloy. So it is not applicable to piston alloy or the hyper-eutectic alloy. Any other question?
Sir, from Mr. Puvendra Kumar, actually, what inert gas you prefer for slag cleaning instead of flux?
Inert gas cannot clean slag. You have to melt the metal. You have to procure clean metal and melt it under cover of inert gas so that oxide or slag is not created at all.
Okay.
Yes.
From Mr.
Once the oxide is created, once the oxide is generated, it has to be chemically removed by flux. The purpose or the Japanese technology says that you do not create the oxide itself. So you have not to remove it. And that's where the inert gas cover or inert gas chamber or vacuum chamber comes into picture. If you have got pre-cleaned ingots, then you melt it in vacuum or in inert gas so that oxide is not formed at all.
Okay, sir.
Next question.
Yeah, any
Next
questions?
question.
Okay, next question is actually from Nilesh Bhagwat. Actually, he said, could you please suggest process for cleaning of machining burr and scrap?
Can you repeat again?
Could you please suggest process for cleaning machining burr, scrap?
Cleaning machining burr or scrap is very difficult task. You have to keep it separate from the beginning itself. Once it is mixed with any other material, it is very difficult to separate. So you have to dedicate one particular machine to one particular alloy segment. That is point number one. Point number two, during changeover, if you want to use the same machine for any other alloy or any other metal, you have to thoroughly clean the machine bed and the cooling tank and all the system wherever that machining chip, those chips are accumulated. Then only you can keep the scrap separate. With such a scrap, the contamination is water and oil. Then by centrifugal force, just like your centrifugal dryer in your washing machine, you can separate out the water and oil in it. Furthermore, you can place it on large trays in open air or in hot atmosphere inside the foundry, so that the further water content is removed from that. And then you can charge it into the furnace. You can go for briquetting also. During briquetting itself, by the immense hydraulic pressure, a lot of oil and water is expelled out and you get a fairly dry briquette. But it is difficult to separate two different alloy burr or two different alloy chips mixed together. Next question.
Sir, from team Altec Technocraft, actually, they asked a question on has ultrasonic degassing been successfully implemented in India?
No. Ultrasonic cleaning is successfully implemented in India. Ultrasonic degassing is not successful. Ultrasonic mixing or ultrasonic alloying is also not successful. It is in laboratory scale only. But ultrasonic cleaning is successful on commercial scale or industrial scale also.
Okay. There was a question from Mr. Bhaskar. In GDC, how frequent we need to clean the die and coat for quality castings?
It depends on quality of the coating. If you are using commercial coatings like die coat 140 or equivalent, then usually you have to touch up after every 4 or 5 shots. And you have to clean the die after 8 hours. But if you are using good quality coatings like 3600 or 1400 or Adele make coatings, then these coatings last for 4000, 5000 shots without any touch up. And hence cleaning is not required for that time period. If you are using such advanced coatings, then usually the die cleaning is performed on the holiday or at the beginning of the next week. Because the die cleaning and recoating process itself is a tedious job. It takes about 2 to 3 hours. Hence it is done once a week and usually such coatings last for the whole week. But for commercial coatings, you have to touch it up after every 4 or 5 shots. And naturally the coating thickness builds up due to such excessive coating. And you have to clean it at every 8 hours or very frequent cleaning. Next question.
Yeah, he also asked one more question, how to control the oxidation on molten metal while continuous pouring of metal treatment.
Okay, you have to keep on adding the covering flux on the molten surface. And during bailing out or scooping out, whenever the ladle enters the metal, it displaces that flux layer and takes up only the clean metal. So continuous application of small quantity of covering flux is recommended for a prolonged holding period. Next question.
Okay, There was one question from Mr. Kunal Bandari. So, in copper alloys, what would be the most recommended method for metal extraction from dross, melting or pulverizing?
Pulverizing. First you
Pul-
have to pulverize the dross, get the metallic granules separated, then wash it clean with water, dry it thoroughly, and then mix it along with some heel metal in viscous condition. Do not put it into fluid or highly liquid metal. Put the recovered particles from dross in the metal when the metal is viscous. Keep the density just like Shrikhand and keep on stirring it on continuous heat and continuous stirring. You will achieve more than 90% recovery from the dross, from the metallic content of the dross. Next question.
Okay. Yeah, there's one more question from Altec. So, in sodium silicate bonded sand process for aluminum castings, what role
Yeah.
mold heating plays in pinholes? Also, what would be the ideal temperature for sand mold and chill at the time of mold pouring?
Okay, sodium silicate is aqueous solution. So there is water of dilution present as well as water of crystallization present in sodium silicate. So recommended temperature of mold heating is 120 to 150 degrees Celsius. You have to keep it at that temperature for minimum of 15 to 20 degrees so that at least 1 centimeter depth of the mold is free from diluting water. The water of crystallization cannot evaporate at that temperature. So you have to take a chance with that. Or you have to apply insulative coating, non-permeable coating on it, which is usually zirconia coating. The chill temperature, again, it should be preheated just like the same thing, 120 to 150 degrees Celsius. Chill should be rust free. That you have to ensure. Whenever you are heating the system of chill and sodium silicate sand together, the water from sand deposits or condensates on the chill. And hence you have to repeat the heating process twice or thrice, so that the total water along with the condensed water, both the water is evaporated and you get the dry mold as well as dry chill. And the chill should be at a temperature more than 120 degrees Celsius for minimum 20 minutes. And once it is fairly cooled to the tune of 80 to 90 degrees Celsius, then it is good time to close the mold. Then you can pour the mold immediately. No problem with that. Next question.
So there's last two questions actually. One is from Mr. Pradeep. How long does degassing refining modification effectiveness last in terms of time?
Okay, in case of humid or highly humid condition, the effect of degassing lasts only for 30 minutes. That is why I have recommended the density index sample to be checked every 30 minutes. The grain refinement, if it is done by metallic grain refiner of titanium boron, and you are not exceeding a temperature more than 780 or preferably 760, then the effect lasts for about 1 hour or so. The modification, if it is done by strontium, then the effect lasts for about 3 to 4 hours. If modification is done by sodium, then the effect lasts only for 20 to 30 minutes.
Okay,
Next
sir.
question.
The other question is from Mr. Bhaskar again. Actually, could you suggest a chill coating to control shrinkage of casting where we use cell core?
Okay, there are three types of coatings which can be conductive, or you can call it partially chilling coatings. First is graphite coating, wherein due to its good conductivity, it transfer heat to a larger surface area. It's slightly chilling in nature. Second one is tellurite paste. People use it very often with ferrous castings, but there is a grade of tellurite paste for non-ferrous or aluminum applications also, which gives a chill depth of about 2 to 3 mm. And another chilling coating is of aluminum powder paste. You get aluminum powder, you have to make it paste in any paint oil or paint thinner and apply it on the core. But ensure that the oil content or the organic material content is evaporated or burnt off before placing the core in the mold. Next question.
Sir, actually, this last question is there. Actually, I think Mr. Hitesh Rathod, actually, can chemically bonded sand like phenolic or alpha set sand system can be used for molds and core for aluminum castings?
Yes, it can be. It can be very well used. No problem with it. Any organic binder leads to combustion, and that combustion leads to release of hydrogen. Hence, that hydrogen can dissolve into molten aluminum, and if the mold filling time is high, then it may create pinhole porosity, which is created inside the mold. So again, you have to coat the mold or core with non-permeable coating like zirconia coating to ensure that that combustion material is not coming in contact with the molten aluminum. Any other question?
Sir, this was the last question.
Okay.
Okay, I'll deliver my vote of thanks actually. Anant sir,
Sure.
thank you very much actually for your excellent presentation. And I think actually this is the, like, after a long time, I'm seeing so many questions, and you were able to answer all the questions actually. Thank you for your time, and we appreciate you on behalf of IAF chapter and Andhra chapter actually.
Thank you very much.
Once again, I thank all the participants here for actively participating in this webinar, and we look forward actually for such sessions in future too. Thank you once again. Thank you.
Thank you. Bye.
Thank you, sir. Bye.
Thank you, sir.
Thank you, sir.